Picture this, a universe so young, so raw, that light itself is just learning to dance. Billions of years before galaxies spun into their familiar shapes, before stars like our sun flickered to life, there was only an endless sea of darkness, thick with secrets. And somewhere in that primordial night, something strange may have stirred, not stars as we know them, but something far more mysterious. Objects so bizarre, they defy everything we thought we understood about how the cosmos works. These are dark stars, not the twinkling lights we see today, but colossal, shadowy giants fueled by an invisible force, dark matter itself. If they existed, they could rewrite the very story of our universe's birth. So tonight, as you settle in, let your mind wander through that ancient darkness. Imagine drifting past these ghostly behemoths, their faint glow whispering clues about a time before time. Where are you joining us from, and what does the night sky look like there? Because together, we're about to journey back, way back, to a universe so different, it might as well be a dream. And who knows, by the time we're done, you might just see the cosmos in a whole new light. Now, let's pull back the curtain on these enigmatic objects. Dark stars aren't just another cosmic oddity. They're a radical reimagining of how the universe might have worked in its earliest days. Unlike the stars we know today, which shine by fusing atoms in their cores, dark stars would have drawn their energy from something far more elusive, the annihilation of dark matter. Picture a star, not burning, but glowing faintly as invisible particles collide and release energy deep within it. This isn't science fiction. It's a serious scientific hypothesis that could solve some of the biggest puzzles about our cosmic origins. What makes dark stars so fascinating is their potential role in the universe's infancy. If they existed, they'd be cosmic pioneers, lighting up the darkness long before ordinary stars had a chance to form. Their sheer size would dwarf anything in the modern universe. Some theories suggest they could grow hundreds of times larger than our sun, yet glow with only a fraction of its brightness. And because they'd rely on dark matter, they might have lasted far longer than conventional stars, quietly shaping the cosmos in ways we're only beginning to understand. But why does this matter? Think of dark stars as missing pieces in the grand puzzle of cosmic evolution. They could explain how the first supermassive black holes formed so quickly, or why certain regions of the early universe seem oddly bright. Most importantly, they remind us that the universe's story is far from complete, and that some of its most thrilling chapters might still be hidden in the shadows. So as we drift deeper into this mystery, keep in mind, dark stars aren't just about rewriting textbooks. They're about unlocking a universe we never knew existed. To truly grasp the wonder of dark stars, we need to step back in time, way back. Imagine the universe not as the vast, star-studded expanse we know today, but as a swirling, seething ocean of raw energy. In those first moments after the Big Bang, everything was packed into an unimaginably dense and hot soup of particles. The cosmos was a turbulent place, where matter and energy collided violently, and the very fabric of space was still settling into shape. This was the perfect breeding ground for dark stars. Unlike today's universe, where matter is spread thin and stars form in isolated pockets. The early cosmos was a crowded, chaotic playground. Dark matter, the invisible scaffolding of the universe, was everywhere, clumping together in dense clouds. Under these extreme conditions, dark stars could have taken root, drawing fuel from the annihilation of dark matter particles in their cores. Picture them glowing softly in that primordial darkness, not with the fierce nuclear fires of modern stars, but with a steady, eerie light born from the unseen. Now, fast forward to the present. The universe has expanded and cooled, stretching out into the relatively quiet, spacious realm we observe today. Stars now form from collapsing gas clouds, igniting through fusion and burning bright but brief lives. Dark stars, if they existed, would be relics of a wilder, more intense era, a time when the rules of cosmic physics were still being written. The contrast couldn't be starker. Today's stars are like campfires in a vast night, while dark stars would have been slow-burning embers in a universe still cloaked in heat and mystery. This journey from the early universe to now isn't just about scale or temperature. It's about possibility. The conditions that might have birthed dark stars are gone, but their legacy could still be written into the cosmos, waiting for us to uncover it. And as we piece together those clues, we're not just studying the past. We're rediscovering a universe far stranger and more wonderful than we ever imagined. Now, let's turn our attention to the silent force that could have shaped these enigmatic dark stars, dark matter itself. Picture an invisible hand guiding the cosmos, unseen yet undeniably powerful. Dark matter doesn't emit light or interact with the electromagnetic force, making it utterly invisible to our telescopes. Yet, its presence is felt everywhere, from the way galaxies spin to the way clusters of galaxies bend light around them. It's the universe's hidden scaffolding, holding everything together without ever revealing itself directly. What makes dark matter so mysterious is its refusal to play by the rules we're familiar with. Unlike ordinary matter, which forms stars, planets, and even us, dark matter doesn't clump together in the same way. It doesn't collide or scatter light. It simply passes through everything, like a ghost drifting through walls. But in the early universe, where conditions were unimaginably dense, dark matter could have piled up in vast, swirling clouds. Inside these clouds, particles of dark matter might have collided and annihilated each other, releasing bursts of energy. And that's where dark stars come in. Imagine a star not powered by nuclear fusion, but by the slow, steady annihilation of dark matter particles. This process could have given dark stars their faint, enduring glow, allowing them to shine for millions or even billions of years. Unlike regular stars, which burn out when their fuel is exhausted, dark stars might have flickered on far longer, sustained by the endless supply of dark matter in their cores. Yet, for all its potential role in shaping the early universe, dark matter remains one of cosmology's most stubborn puzzles. We know it exists because of its gravitational effects, but we still don't know what it's made of. Is it a yet undiscovered particle, a shadowy counterpart to the matter we know, or something even stranger? Every experiment designed to detect it has come up empty, leaving scientists to piece together clues from the cosmos itself. This elusive nature is what makes dark matter, and by extension, Dark stars so fascinating. They challenge our understanding of the universe, forcing us to rethink what's possible. And as we continue to search for answers, we're reminded that the cosmos is far more mysterious than it appears. The story of dark stars isn't just about the past. It's about the unanswered questions that still linger in the darkness, waiting to be uncovered. Now, let's step back in time to uncover how the idea of dark stars first took root in the minds of scientists. The story begins with a bold question. What if the earliest stars weren't like the ones we see today? In the early 2000s, a team of astrophysicists, led by Catherine Fries, began piecing together a radical theory. They proposed that dark matter, not just ordinary gas and dust, could have fueled the first stars in the universe. Fries and her colleagues realized that in the dense, hot environment of the early cosmos, dark matter particles might have clustered tightly enough to collide and annihilate, releasing energy. This process could have created objects unlike anything in the modern universe, stars glowing faintly from dark matter's hidden fire. Their work wasn't just speculative, it was grounded in the math of particle physics and cosmology, bridging two of science's biggest mysteries, the nature of dark matter and the origins of the first stars. What made this theory so groundbreaking was its challenge to conventional wisdom. Until then, astronomers assumed the first stars were powered by nuclear fusion, just like the sun. But Fries's team showed another possibility, one where dark matter's invisible energy could have shaped the cosmos in ways we're only beginning to imagine. Their calculations suggested these dark stars could have grown to staggering sizes, hundreds of times more massive than our sun, yet glowing with a cooler, subtler light. Of course, every new idea faces skepticism. Some researchers questioned whether dark matter could clump densely enough to form stars, or whether annihilation would produce enough energy to sustain them. But Fries and her collaborators pressed on, refining their models and addressing doubts. Over time, their work gained traction, inspiring others to explore the tantalizing implications. Could dark stars have been the universe's first light? Might their remnants still linger in the cosmos today? The legacy of this theory isn't just about answering old questions, it's about opening new ones. By daring to rethink how stars form, Fries and her team reminded us that the universe often hides its most extraordinary secrets in plain sight. And as we continue to probe the shadows of the cosmos, their work lights the way forward, urging us to look beyond what we think we know. Now, let's shine a light on what truly sets dark stars apart from the stars we know today. Imagine a star that doesn't burn in the way you'd expect, no fiery nuclear fusion at its core, no blistering heat like our sun. Instead, picture an object glowing softly, powered by something invisible, the annihilation of dark matter particles. That's the essence of a dark star. While regular stars, like our sun, rely on the fusion of hydrogen into helium to produce energy, dark stars draw their power from the collisions of dark matter particles, releasing energy in a slow, steady process. This fundamental difference in energy source creates stars with entirely unique properties. Take size, for example. The largest stars in today's universe are already mind-bogglingly big, but dark stars could have dwarfed them. Theoretical models suggest these cosmic oddities might have grown hundreds of times more massive than our Sun, yet without the searing temperatures of ordinary stars. Their cooler, dimmer glow would have given them an eerie, almost ghostly appearance far from the brilliant pinpricks of light we see in the night sky. Then there's the question of lifespan. Nuclear fusion burns hot and fast, causing regular stars to exhaust their fuel relatively quickly, at least on cosmic timescales. But dark stars, fueled by the gradual annihilation of dark matter, could have lasted much longer, potentially even surviving into the present day, hidden in the vast reaches of space. And let's not forget luminosity. A dark star's light wouldn't come from the intense radiation of fusion, but from the quieter, more diffuse energy of dark matter interactions. This means they'd emit light differently, possibly peaking in the infrared spectrum rather than the visible light we associate with stars. If they still exist, spotting them would require looking for the faintest whispers of warmth in the darkness, a task as challenging as it is thrilling. So while both dark stars and regular stars illuminate the cosmos, they do so in ways that couldn't be more distinct. One burns bright and fast, the other glows slow and steady, a reminder that the universe has more than one way to light up the darkness. Now, let's take a closer look at the engine that powers these mysterious dark stars, the annihilation of dark matter itself. Picture two invisible particles drifting through space, drawn together by gravity. When they collide, something extraordinary happens. They don't just bounce off each other or merge quietly. Instead, they annihilate, vanishing in a burst of pure energy. This process is the heartbeat of a dark star, the secret behind its gentle, enduring glow. Unlike the violent nuclear fusion in regular stars, where atoms smash together under extreme pressure, dark matter annihilation is a quieter affair. The particles involved, often theorized to be WIMP or weakly interacting massive particles, cancel each other out upon contact, converting their mass directly into energy. This energy then heats the surrounding gas, creating a stable, long-lasting light source. It's a slow burn, more like the steady warmth of embers than the roaring blaze of a fire. What makes this so fascinating is the sheer efficiency of the process. In a regular star, fusion requires incredibly high temperatures and pressures to overcome the repulsion between atomic nuclei. But dark matter annihilation doesn't face those same hurdles. Dark matter particles, if they exist as we suspect, don't interact with light or ordinary matter the way atoms do. They can pass right through each other until they collide and annihilate, releasing energy without the need for extreme conditions. This unique mechanism gives dark stars their remarkable stability. While fusion-powered stars eventually run out of fuel, dark stars could keep shining as long as there's dark matter to feed them. Imagine a cosmic candle that never burns down, glowing faintly for billions of years. That's the potential of annihilation-powered light, a phenomenon unlike anything we see in the universe today. And here's the twist. This process might even explain why dark stars could grow so enormous. With a nearly endless fuel supply, they could accumulate vast amounts of gas and dark matter, ballooning to sizes that defy our expectations. Their light wouldn't flicker or flare, but remain steady, a quiet testament to the invisible forces shaping the early cosmos. So while annihilation might sound like destruction, in the case of dark stars, it's the key to creation, a subtle, persistent power source that challenges everything we know about how stars live and shine. Now, let's turn our gaze to the present and ask a tantalizing question. Could dark stars still be out there, lurking in the cosmos today? It's a possibility that stretches the imagination. These ancient objects, born in the early universe, might have survived the eons, hidden in the vast darkness between the stars we know. If dark stars exist now, they'd be incredibly faint compared to their younger selves. Their glow would come from the slow, steady annihilation of any remaining dark matter, a dim ember in the cosmic night. But here's the catch: finding them would be like searching for a whisper in a storm. Without the brilliant light of fusion, they'd blend into the background, invisible to traditional telescopes. Astronomers aren't giving up, though. One way to spot them could be through their heat signature. Even a faint dark star would emit some infrared radiation, a subtle warmth that powerful instruments like the James Webb Space Telescope might detect. Another clue could come from their gravitational influence. If a dark star is massive enough, it could bend light around it, a phenomenon called gravitational lensing, revealing its presence indirectly. There's also the chance that dark stars didn't survive at all. Over billions of years, their dark matter fuel might have been exhausted, causing them to collapse into black holes or simply fade away. Yet if even a handful endured, they'd be cosmic relics, offering us a direct window into the universe's infancy. The hunt for these elusive objects is more than just a scientific curiosity. It's a test of our understanding of dark matter itself. Finding a dark star today would confirm not only their existence, but also the strange, invisible particles that power them. So while the search is daunting, the reward could rewrite the story of our universe. And with that, we edge closer to the next mystery: how modern technology might finally bring these shadowy giants into the light. Now, let's explore the fascinating challenge of actually detecting these cosmic phantoms. The search for dark stars isn't just about knowing where to look, it's about figuring out how to see the invisible. Since dark stars don't shine like ordinary stars, traditional telescopes, designed to capture visible light, would pass right over them without a clue. This forces astronomers to get creative, turning to indirect methods and cutting-edge technology to uncover their secrets. One promising approach is gravitational lensing. Imagine a dark star drifting in front of a distant galaxy. Its immense gravity would warp the fabric of space-time, bending the light from that galaxy like a magnifying glass. By studying these subtle distortions, scientists might pinpoint the dark star's presence, even if it emits no light of its own. It's like finding a hidden object by the shadow it casts, a cosmic game of hide and seek played across the universe. Then there's the infrared approach. While dark stars wouldn't blaze with the heat of nuclear fusion, the slow annihilation of dark matter within them would still produce a faint warmth. Telescopes like the James Webb Space Telescope, equipped with ultra-sensitive infrared detectors, could scan the skies for these elusive heat signatures. Think of it as trying to spot a dying ember in a vast, dark room. Only the most advanced instruments stand a chance. But even these methods come with hurdles. Gravitational lensing events are rare and require precise alignment between the dark star, a background light source, and our line of sight. Infrared surveys, meanwhile, must contend with countless other warm objects in space, from distant galaxies to cosmic dust clouds. It's a needle in a haystack problem on an astronomical scale. Despite the challenges, the pursuit of dark stars pushes the boundaries of what's possible in astronomy. Every failed search narrows the possibilities, and every new tool, like next-generation telescopes or advanced data analysis techniques, brings us closer to solving the mystery. And if we do succeed, the discovery won't just reveal dark stars. It'll open a new chapter in our understanding of dark matter itself. With that in mind, let's turn our attention to another captivating idea: how these enigmatic objects might have shaped the very first light in the universe. Now, picture the universe in its earliest moments, a vast, dark expanse, just beginning to stir with the faintest glimmers of light. This is where dark stars might have played a role unlike any other. Long before the first conventional stars ignited, these mysterious objects could have been the pioneers, casting the universe's first glow. Unlike regular stars, which rely on nuclear fusion, dark stars would have drawn their energy from the annihilation of dark matter particles. This process would have produced a steady, gentle light more like a cosmic ember than the blazing furnaces we associate with stars today. But in a universe still shrouded in darkness, even that faint glow would have been revolutionary. Imagine standing in a pitch-black room and lighting a single candle. That's the kind of impact dark stars might have had, tiny beacons piercing the endless night. What makes this idea so compelling is the timeline. The first conventional stars, known as population 3 stars, took time to form. They needed dense clouds of hydrogen and helium to collapse under gravity, a process that could have taken millions of years. But dark stars, fueled by dark matter, might have formed much earlier. Dark matter was everywhere in the young universe, clumping together quickly under its own gravity. This means dark stars could have flickered to life while the cosmos was still in its infancy, lighting the way for everything that followed. Their light wouldn't have been bright or flashy, but it would have been constant. While conventional stars burn fiercely and die young, dark stars could have shone for millions, even billions of years. This endurance might have allowed them to influence the universe in ways we're only beginning to understand. For instance, their steady radiation could have helped shape the distribution of matter, nudging gas clouds into the right places for future star formation. And here's the most intriguing part. If dark stars were among the first sources of light, they might hold clues about one of cosmology's biggest puzzles: the epoch of reionization. This was the period when the universe transitioned from a fog of neutral hydrogen to the transparent cosmos we see today. Conventional stars are often credited with driving this change, but dark stars could have played a supporting role, their faint light helping to ionize the surrounding gas over vast stretches of time. Of course, this is all still theoretical, but it's a reminder of how much we still have to learn about the universe's earliest chapters. Dark stars, if they existed, wouldn't just be curiosities, they'd be key players in the story of cosmic dawn. And as we piece together their possible role, we're not just uncovering the past, we're shedding light on the invisible forces that shaped everything around us. With that in mind, let's turn to another fascinating possibility: how these ancient objects might have set the stage for the supermassive black holes that dominate galaxies today. Now, let's explore one of the most intriguing possibilities: how dark stars could have been the hidden architects behind the supermassive black holes we see today. These cosmic giants, lurking at the centers of galaxies, have puzzled scientists for decades. How did they grow so massive, so quickly, in the early universe? Dark stars might hold the answer. Picture this: a dark star, fueled by dark matter annihilation, grows larger and more massive over time. Unlike regular stars, which eventually exhaust their fuel and collapse, dark stars could have kept shining for billions of years, accumulating staggering amounts of matter. Eventually, when their dark matter fuel ran out, these behemoths might have collapsed under their own gravity, not into a supernova, but directly into a black hole. And not just any black hole, we're talking about seeds for the supermassive monsters we observe today. This idea solves a major cosmic mystery. Conventional theories struggle to explain how supermassive black holes formed so early in the universe's history. By the time the first galaxies were taking shape, these black holes were already billions of times the mass of our sun. That's like finding a fully grown oak tree in a freshly planted garden. But if dark stars existed, their collapse could have provided the perfect starting point: a massive seed that grew rapidly by devouring surrounding gas and merging with other black holes. There's another twist. Dark stars wouldn't just collapse into black holes quietly. Their immense size and unique structure could have created conditions unlike anything in the modern universe. Imagine a star hundreds of times wider than our solar system, packing enough mass to warp spacetime itself. When it finally collapsed, the resulting black hole would have been born with a head start, already primed to grow into the giants we see today. Of course, this is still theoretical, but it's a compelling piece of the puzzle, connecting the faint glow of dark stars to the shadowy titans at the heart of galaxies. And if future observations or simulations confirm this link, it would rewrite our understanding of how the universe's most mysterious structures came to be. With that in mind, let's shift our gaze to how scientists are using cutting-edge technology to bring these cosmic mysteries into focus. Now, let's step into the virtual laboratories where scientists bring dark stars to life, not through telescopes, but through the power of computer simulations. These digital experiments allow researchers to recreate the extreme conditions of the early universe, testing how dark stars might have formed, evolved, and ultimately shaped the cosmos. Imagine feeding the laws of physics into a supercomputer, along with our best guesses about dark matter's behavior. Scientists input variables like temperature, density, and the rate of dark matter annihilation, then watch as virtual dark stars emerge on screen. These simulations reveal something astonishing. Dark stars could have grown to sizes almost unimaginable by today's standards. Some models suggest they might have reached widths thousands of times larger than our sun, glowing faintly with the energy of colliding dark matter particles. One of the biggest challenges, dark matter itself remains a mystery. Without knowing exactly how it interacts, simulations have to explore a range of possibilities. Some show dark stars forming in dense pockets of dark matter, growing steadily as they pull in more material. Others suggest these objects could have been short-lived, collapsing quickly if their dark matter fuel was sparse. But even these conflicting results help narrow down what to look for in real observations. The most revealing simulations focus on structure. Unlike regular stars, which have fiery cores and turbulent surfaces, dark stars might have been eerily uniform, smooth spheres of hydrogen and helium, heated evenly by dark matter annihilation. Some models even propose layered interiors, with dark matter concentrated at the core, creating a gentle but persistent energy source. These details are crucial because they hint at how dark stars could have influenced their surroundings, seeding galaxies or even those supermassive black holes we discussed earlier. Of course, simulations aren't perfect. They rely on assumptions, and tweaking just one variable can lead to wildly different outcomes. But each run brings us closer to understanding whether dark stars are more than just a beautiful theory. And as supercomputers grow more powerful, these virtual universes will become even more precise, perhaps one day matching the faint signals we detect in the night sky. With these digital blueprints in hand, let's turn to another piece of the puzzle: how dark stars compare to the universe's very first generation of stars, known as population 3 stars. Now, let's untangle the cosmic puzzle of how dark stars stand apart from the universe's earliest stellar pioneers, population 3 stars. While both types of objects emerged in the young cosmos, their origins and behaviors couldn't be more different. Population 3 stars were the first true stars, blazing to life from pristine hydrogen and helium alone. They were massive, short-lived giants, burning bright through nuclear fusion before exploding as supernova, seeding the universe with heavier elements. But dark stars, they operated on an entirely different cosmic rulebook. Instead of fusion, they drew energy from the annihilation of dark matter particles, glowing with a cooler, steadier light. Here's the key distinction. Population 3 stars were like cosmic fireworks, intense, brilliant, and fleeting. Dark stars, by contrast, might have been more like slow-burning embers, potentially lasting far longer because their dark matter fuel could have sustained them for millions or even billions of years. Their size also sets them apart. While population 3 stars were enormous by today's standards, dark stars could have dwarfed them, growing to colossal scales thanks to their unique energy source. Another critical difference lies in their legacy. Population 3 stars died violently, scattering elements that built later generations of stars and planets. Dark stars, if they existed, might have met quieter fate, perhaps collapsing directly into black holes without explosive deaths, or simply fading as their dark matter fuel ran out. This contrast isn't just academic. If dark stars existed alongside population 3 stars, they could have shaped the early universe in unseen ways, altering how galaxies formed, or even providing the seeds for supermassive black holes. It's a reminder that the cosmos might have hosted more variety in its infancy than we ever imagined. With this distinction clear, We can now ponder another intriguing question. Just how long could these mysterious dark stars have endured? Now, let's turn our attention to the remarkable longevity of dark stars, how these cosmic anomalies might have defied the usual life cycles of ordinary stars. Unlike the brief, fiery existence of population, 3 stars, dark stars could have thrived for staggering lengths of time, all thanks to their unconventional fuel source. Picture this: while a typical massive star might burn out in just a few million years, a dark star could have glowed steadily for billions. The secret lies in dark matter annihilation, a process far more efficient and enduring than nuclear fusion. Instead of exhausting its fuel quickly, a dark star would have consumed its dark matter supply at a slow, steady pace, like a candle that refuses to flicker out. But here's where it gets even more fascinating. Some theories suggest that if dark stars formed in regions rich with dark matter, they might have lasted even longer, perhaps surviving well into the era when modern galaxies began taking shape. Imagine a dark star shining faintly in the cosmic dawn, outliving entire generations of regular stars. Of course, their lifespan wouldn't have been infinite. Eventually, the surrounding dark matter would have thinned out, leaving these giants with nothing to sustain them. They might have collapsed silently into black holes, or simply faded into darkness, leaving no explosive trace behind. This raises another tantalizing possibility. Could remnants of dark stars still linger in today's universe? While they'd be incredibly difficult to spot, their influence might hide in plain sight, perhaps as unexplained gravitational anomalies or mysterious infrared glows. As we ponder their endurance, one thing becomes clear: dark stars challenge our very understanding of stellar life and death. They remind us that the universe, in its infancy, might have been far stranger and far more patient than we ever dreamed. With this in mind, let's explore how these enigmatic objects could have shaped one of the universe's most pivotal chapters, the era of reionization. Now, let's journey into one of the universe's most transformative periods, the reionization era, and uncover how dark stars might have played a starring role. This cosmic turning point, when the fog of neutral hydrogen that filled the early universe was burned away by the first sources of light, reshaped everything. And dark stars, with their eerie glow and immense longevity, could have been key players in this grand transition. Imagine the early cosmos as a vast, murky ocean. For hundreds of millions of years after the Big Bang, it was filled with neutral hydrogen gas, absorbing light and keeping the universe dark. Then, something began to change. Radiation from the first luminous objects started to strip electrons from these hydrogen atoms, ionizing them and clearing the cosmic fog. But here's the twist: conventional stars alone might not have had enough power or time to complete this process. That's where dark stars enter the picture. With their ability to shine for billions of years, dark stars could have provided a steady, pervasive light source, bathing the universe in ionizing radiation far longer than ordinary stars. Their unique energy source, dark matter annihilation, would have made them incredibly efficient at this task, like cosmic lighthouses piercing the primordial gloom. Some theories even suggest that dark stars might have been the dominant sources of light during reionization's early stages, setting the stage for later generations of stars to finish the job. But their influence wouldn't have stopped there. The sheer size of dark stars, potentially millions of times larger than our sun, meant they could have ionized vast regions of space around them, creating bubbles of transparency in the hydrogen fog. These bubbles might have acted as cosmic nurseries, allowing light from later stars to travel farther and accelerate reionization. Yet, mysteries remain. If dark stars were so influential, why haven't we found direct evidence of them yet? The answer might lie in their quiet demise. Unlike supernova, which announced their deaths with brilliant explosions, dark stars likely faded or collapsed without fanfare, leaving behind subtle clues in the cosmic microwave background or the distribution of galaxies. As we piece together this cosmic puzzle, one thing is certain: dark stars challenge our understanding of how light first conquered the darkness. They remind us that the universe's greatest transformations might have been driven by objects we're only beginning to imagine. Next, we'll consider other possible explanations for the early universe's light and why dark stars remain a compelling piece of the puzzle. While dark stars offer a fascinating explanation for the first light in the cosmos, they aren't the only candidates scientists have considered. Let's explore some of the other leading theories that attempt to solve this cosmic mystery and why dark stars still stand out as a unique possibility. One prominent alternative points to quasars, the brilliant cores of distant galaxies powered by supermassive black holes. These cosmic powerhouses emit staggering amounts of radiation, easily capable of ionizing hydrogen across vast distances. But there's a catch. Quasars require fully formed galaxies and mature black holes, which might not have existed early enough to trigger reionization all on their own. Another contender is the universe's first generation of regular stars, known as population 3 stars. These giants, born from pure hydrogen and helium, burned hot and fast, flooding space with ultraviolet light. However, their short lifespans, just a few million years, raise questions about whether they could have sustained reionization long enough to clear the cosmic fog entirely. Then there's the possibility of early galaxies packed with countless smaller stars working together. While plausible, this scenario struggles to explain how enough light escaped these dense stellar nurseries to ionize the wider universe. Dust and gas within galaxies tend to absorb radiation, making it harder for light to break free and do the job. What makes dark stars so compelling, despite these alternatives? Unlike quasars or population 3 stars, dark stars could have shone steadily for billions of years, providing a persistent and widespread light source. Their sheer size and unique energy mechanism would have allowed them to ionize vast regions without the limitations of short lifespans or dense galactic environments. That said, the search isn't about declaring one theory the winner. The early universe was likely lit by a combination of sources, each contributing in its own way. Dark stars simply fill gaps that other explanations can't, offering a missing piece to the puzzle of how light first triumphed over darkness. As we continue to probe the cosmos, the truth may lie in a tapestry of these ideas, woven together by time and discovery. But for now, Dark stars remain one of the most intriguing threads in that cosmic story. Next, we'll turn to the skeptics, those who challenge the dark star hypothesis, and examine the healthy debate that drives science forward. Now, let's step into the realm of scientific debate, where even the most captivating ideas face scrutiny. While dark stars present an elegant solution to cosmic mysteries, not all researchers are convinced they are the missing piece of the puzzle. Skepticism, after all, is the engine of discovery pushing theories to prove their worth. One major critique centers on the very foundation of dark stars, dark matter itself. We still don't know the exact nature of dark matter particles, let alone whether they could annihilate in the way the theory suggests. Without direct evidence of these particles' behavior, some argue that dark stars remain a beautiful hypothesis built on unknown physics. Others point to the lack of observational evidence. Despite decades of searching, no telescope has definitively spotted a dark star. Critics argue that if these objects were as massive and long-lived as proposed, we should have found hints of them by now, especially in the faint glow of the early universe. The absence of such signals leaves room for doubt. There's also the challenge of explaining how dark stars would form in the first place. Simulations show they'd need incredibly dense pockets of dark matter, conditions that might have been rare even in the early cosmos. Without a clear mechanism for gathering dark matter into such tight clusters, the theory relies on assumptions that aren't yet proven, and let's not forget the competition. Some scientists believe that more conventional explanations, like supermassive black holes or exotic stellar phenomena, could account for early cosmic light without invoking dark stars. These alternatives may not solve every puzzle, but they're grounded in physics. We already understand making them a safer bet for many researchers. Yet this skepticism isn't a dismissal. It's a call for better evidence, sharper models, and deeper exploration. Every challenge to the dark star idea pushes its supporters to refine their arguments, test new predictions, and search harder for proof. That's how science progresses, not by clinging to ideas, but by stress testing them until only the strongest survive. So where does that leave us? In the vibrant, sometimes messy arena of cosmic debate, where even the most promising theories must earn their place. Next, we'll look at the subtle clues that might still tip the scales in favor of dark stars, hidden in the faint whispers of the universe itself. But even in the absence of direct sightings, the universe leaves behind breadcrumbs, subtle hints that might point us toward dark stars. Let's explore the indirect evidence that keeps this tantalizing idea alive. One promising clue lies in the cosmic microwave background, the faint afterglow of the Big Bang. Tiny irregularities in this ancient light could hold signatures of dark stars. Some theorists suggest these objects, with their unique heat and energy output, might have left distinct imprints on the early universe's structure. It's like finding a fingerprint on a dusty window. We can't see the hand that left it, but the mark tells a story. Then there's the mystery of unexplained infrared signals from the distant cosmos. Certain patches of the early universe glow a bit brighter than expected in infrared light, and no known type of star fully accounts for it. Could these be the fading embers of dark stars, radiating heat long after their dark matter fuel waned? It's a long shot, but an intriguing possibility. Gravitational lensing offers another indirect path. If dark stars were as massive as predicted, their gravity would bend light from objects behind them, creating telltale distortions. Astronomers have spotted odd lensing effects that don't quite match known galaxies or black holes, leaving room for speculation. Even the distribution of matter in the universe might hold clues. Dark stars, if they existed in large numbers, could have influenced how galaxies clustered in the cosmos' infancy. Some computer models show that adding dark stars to simulations better matches the large-scale structures we observe today. Of course, none of this is proof. Each piece of indirect evidence could have other explanations, and that's the frustrating beauty of cosmology. But together, these hints form a trail, one that keeps researchers searching, refining their tools, and hoping for that break through observation. Next, we'll see how the James Webb Space Telescope is turning hope into action, scanning the skies for answers. Now, let's turn our gaze to a tool that might finally bring these cosmic mysteries into focus: the James Webb Space Telescope. With its unmatched ability to peer into the infrared spectrum, this observatory is like a time machine, allowing us to look deeper into the early universe than ever before. Dark stars, if they exist, would glow faintly in infrared light, a signature that older telescopes simply couldn't detect clearly. But the James Webb Telescope sensitive instruments are designed to pick up these subtle whispers from the cosmos. Imagine trying to spot a candle flickering in a foggy night. Previous telescopes saw only the haze, but Webb cuts through it, revealing details we've missed for decades. One of the telescope's key missions is to study the first galaxies, and in doing so, it might accidentally stumble upon dark stars. These objects could be hiding in plain sight, masquerading as unusually bright or oddly placed points of light in Webb's deep field images. Researchers are already combing through the data, looking for anything that doesn't fit the expected patterns of early stars or galaxies. What makes Webb especially promising is its ability to analyze the chemical makeup of distant objects. If it finds a candidate that lacks the heavy elements typical of regular stars, but emits the right kind of heat, that could be our first real clue. It's like finding a fingerprint that matches no known species, a hint that something entirely new is out there. Of course, even with this technological marvel, the search is like finding a needle in a cosmic haystack. But for the first time, we have a tool sharp enough to make the attempt. Every new image from Webb brings us closer to answering the question: did dark stars light up the infant universe? The next chapter in this story might be written not in theory, but in actual data, and that's what makes this moment so thrilling. While the search for dark stars continues in the realm of science, these mysterious objects have already found a home in the world of stories and imagination. Long before telescopes turned toward the early universe, writers and creators were dreaming up celestial wonders that bear a striking resemblance to these hypothetical giants. Take, for instance, the eerie glow of Mordor's dark towers in fantasy epics, or the ominous dead stars haunting the pages of cosmic horror. These fictional creations often mirror what scientists now theorize about dark stars' objects, radiating an unsettling, otherworldly light. It's as if storytellers glimpsed fragments of a scientific idea before it fully took shape. Science fiction has a knack for borrowing from the edges of real astrophysics, and dark stars are no exception. Some novels imagine them as ancient beacons left by vanished civilizations, while others cast them as cosmic prisons for unspeakable entities. What's fascinating is how often these tales capture the essence of real scientific speculation, objects powered by the invisible hand of dark matter, glowing faintly against the void. Even films and games have toyed with the concept, portraying dark stars as waypoints for interstellar travelers or as the birthplaces of strange new energies. While these versions take creative liberties, they share a thread with actual research: the idea that the universe might hide forms of light and energy beyond our everyday experience. This cultural fascination isn't just coincidence. Dark stars represent the perfect blend of science and mystery, real enough to feel plausible, yet enigmatic enough to spark endless what-if scenarios. They remind us that sometimes the line between cutting-edge theory and compelling fiction is thinner than we think, and who knows, perhaps one day, science will confirm their existence, turning these speculative visions into something even more extraordinary: reality. Until then, dark stars will keep illuminating not just our telescopes, but our stories, dreams, and the boundless curiosity that drives both scientists and storytellers alike. Now, let's turn our gaze toward the horizon of discovery, where the future of dark star research holds thrilling possibilities. Scientists aren't just waiting for answers. They're actively designing tools and missions to hunt for these cosmic ghosts. At the forefront is the James Webb Space Telescope, already peering into the early universe with unprecedented clarity. Its infrared eyes are perfectly tuned to spot the faint, lingering glow of dark stars, if they exist. Every new dataset from Webb could bring us closer to confirming or rewriting our theories, but the search doesn't stop there. Upcoming observatories like the Nancy Grace Roman Space Telescope, set to launch later this decade, will map vast stretches of the sky with even greater sensitivity. Imagine combining Roman's wide-field surveys with Webb's deep zoom, a 1-2 punch that might finally corner these elusive objects. Meanwhile, on the ground, next-generation telescopes like the Extremely Large Telescope will scan the heavens with mirrors so massive they could resolve details of ancient light sources we've only dreamed of studying. Theoretical work is racing ahead too. Researchers are refining models to predict exactly how dark stars should look, down to their chemical fingerprints and energy signatures. Advanced simulations, powered by supercomputers, are testing how these objects form, evolve, and potentially collapse into the seeds of supermassive black holes. Each simulation is like a cosmic lab experiment, helping scientists narrow down where and how to look. And then there are the wild cards, ideas still on the drawing board. Concepts like orbiting gamma-ray detectors, tuned to spot dark matter annihilation signals, or networks of tiny satellites working in unison to scan the sky for anomalies. Some theorists even speculate that dark stars could leave behind distinct echoes in the cosmic microwave background, subtle ripples that future missions might uncover. What's exhilarating is how collaborative this quest has become. Astronomers, particle physicists, and cosmologists are pooling their expertise because cracking the mystery of dark stars could answer bigger questions about dark matter itself. Every new tool, every fresh calculation, brings us a step closer to knowing whether these giants of the early universe are out there waiting to be found. So while dark stars remain hypothetical for now, the next decade of research promises to turn speculation into solid science, whether through a groundbreaking observation or an unexpected twist in the data. The universe might soon reveal one of its best-kept secrets. And when it does, our understanding of cosmic history could change forever. Now, let's stretch our imaginations even further, beyond the edges of our own universe. Could dark stars exist in other realms, part of a vast multiverse? The idea of multiple universes, each with its own unique physics and history, isn't just science fiction. Some theories suggest that if dark stars formed in our early cosmos, they might have cosmic twins elsewhere, glowing in universes with different rules. Picture this: in another universe, dark matter might behave slightly differently, perhaps more abundant or with stronger interactions. There, dark stars could be even larger or longer lived, dominating their skies in ways we can barely fathom. Or maybe in some realms, dark matter doesn't annihilate at all, leaving those universes forever dark, without even the faint glow of these hypothetical giants. The multiverse hypothesis opens wild possibilities. If dark stars exist here, their counterparts elsewhere might hold clues about the nature of reality itself. Some physicists speculate that studying anomalies in our universe, like the unexpected brightness of certain early galaxies, could hint at interactions with other universes where dark stars played a different role. It's a dizzying thought. Our search for dark stars might not just reveal secrets of our cosmos, but echo across the fabric of existence. Of course, this is all speculative, but that's what makes it thrilling. The multiverse idea pushes us to ask bigger questions. Are dark stars unique to our universe, or are they cosmic constants, appearing wherever dark matter and the right conditions collide? As we peer deeper into the mysteries of our own universe, we might just find clues that ripple far beyond it. And with that, we're left wondering, what other surprises might the multiverse hold? The answers, much like dark stars themselves, remain just out of reach for now. Now, let's take a step back and consider what dark stars might mean for us, not just as cosmic curiosities, but as windows into the deepest questions about reality. These mysterious objects don't just defy our expectations about how stars work. They force us to confront the boundaries of what we know and even what we can know. Think about it. Dark stars, if they exist, are powered by something invisible: dark matter, a substance that makes up most of the universe's mass, yet we've never directly seen it. That alone is humbling. It's a reminder that the universe operates on rules we're still piecing together, and that what we call reality might be far stranger than we've ever imagined. Then there's the scale of it all. Dark stars could have been among the first sources of light, shining in a universe that was just taking shape. That means they're not just objects. They're part of the story of how everything came to be. Studying them isn't just about filling gaps in our cosmic timeline. It's about understanding our own origins in a universe that's vast, ancient, and full of secrets. And what if we never find them? That's just as fascinating. The search itself pushes our technology, our theories, and our imaginations to the limit. It shows us where our knowledge ends and where the next great discovery might begin. Whether dark stars are real or not, they've already expanded how we think about space, time, and our place in it all. So as we ponder these hypothetical giants, we're really asking bigger questions. What else is out there, hidden in the darkness? How much of the universe remains beyond our grasp? And what will it mean when, or if, we finally find the answers? The journey to understand dark stars isn't just about astronomy. It's about what it means to explore, to wonder, and to be human in a cosmos that's always one step ahead of us. With that in mind, let's turn to the final chapter of our journey, a moment to unwind and let these ideas drift among the stars. Now, let's close our eyes for a moment and imagine drifting through the silent vastness of space. Picture yourself floating toward a dark star, its presence looming in the distance like a faint, ghostly beacon. Unlike the blazing suns we know, this one glows with an eerie, subdued light, a pale shimmer against the endless black. As you draw closer, the scale of it becomes almost overwhelming. This isn't just a star, it's a colossal sphere, dwarfing anything in our modern universe, its surface radiating a strange, otherworldly warmth. The light it emits isn't the fierce blaze of nuclear fusion, but something softer, more mysterious, powered by the annihilation of dark matter deep within its core. Around you, the cosmos feels different here, quieter, as if the universe itself is holding its breath. The dark star's glow casts long, faint shadows across space, illuminating wisps of primordial gas that swirl like smoke in its gravitational pull. There's a stillness to this place, a sense of witnessing something ancient and rare, a relic from a time when the universe was young and the rules of physics played out in ways we're only beginning to understand. Take a deep breath and let the wonder of it sink in. This is a place where the invisible becomes visible, where dark matter, the hidden architect of the cosmos, reveals itself in the faintest whisper of light. It's humbling, isn't it, to stand at the edge of such a mystery, to glimpse a corner of the universe that defies everything familiar. And as you linger here, let the quiet majesty of the dark star lull you into a deeper calm. Imagine its light wrapping around you, not harsh or blinding, but gentle, like the faintest glow of embers in the dark. This is the universe as it once was, strange, beautiful, and full of secrets, waiting to be uncovered. Now, as we slowly drift away from this cosmic giant, carry that sense of awe with you, because whether dark stars are out there or not, the act of imagining them reminds us how vast, how mysterious, and how breathtaking the cosmos truly is. Now, let's take this journey a step further by adding another layer to our cosmic exploration sound. Imagine the deep, resonant hum of a dark star, a low-frequency vibration that seems to pulse through the void. Unlike the crackling energy of a regular star, this sound would be slow, steady, almost meditative, like the distant echo of a giant bell ringing in the depths of space. Picture the way this sound might mingle with the faint whispers of interstellar gas, swirling around the dark star in slow, ghostly currents. The effect would be haunting yet soothing, a cosmic lullaby composed by the universe itself. If you were to close your eyes and listen, you might hear something akin to a deep choir of drones, layered with the occasional shimmer of high notes, like starlight translated into sound. For those who love ambient music, think of artists like Brian Eno or Stars of the Lid, whose work captures that same sense of vastness and mystery. Their compositions, slow, atmospheric, and immersive, could be the perfect soundtrack to accompany this segment, wrapping you in a sonic blanket that mirrors the dark star's eerie glow. Or perhaps something more organic, like the deep tones of a Tibetan singing bowl, vibrating at a frequency that feels both ancient and timeless. That's the kind of soundscape that would fit here, something that doesn't just play in the background, but pulls you deeper into the experience, making the dark star feel even more real, more tangible. And if you're someone who enjoys the sounds of nature, imagine the distant rumble of thunder, slowed down to a crawl, or the deep, rhythmic crashing of ocean waves on a shore light years away. These earthly sounds, stretched and twisted into something otherworldly, could evoke the same sense of scale and grandeur that a dark star embodies. So as you let your mind wander back to that faint, ghostly beacon in the dark, try adding this layer of sound to your mental journey. Let it fill the silence of space, not as a distraction, but as an enhancement, a way to feel the universe in a way that's both familiar and utterly strange. Because sometimes the most profound discoveries aren't just seen or imagined, they're heard. Now, let's turn the spotlight over to you. Dark stars are still a mystery, a cosmic puzzle waiting to be solved, and that means there's plenty of room for curiosity. What do you think these enigmatic objects might look like if we ever found one? Could they be lurking in the distant corners of the universe, hidden in plain sight? Or maybe you have your own theory about how dark matter fuels them, or what kind of light they'd cast across the cosmos. Drop your thoughts in the comments below, whether it's a wild idea, a burning question, or even a sci-fi inspired vision of what a dark star system might hold. This is your chance to join the conversation, to add your voice to the search for answers, and who knows, maybe your theory will spark a discussion that leads us closer to uncovering the truth. While you're at it, let me know what other cosmic mysteries you'd love to explore next. The universe is full of wonders, and your curiosity helps shape the journey. So don't hold back, share what's on your mind, and let's keep unraveling the secrets of the cosmos together. Now, before we go any further, let's clear up some confusion. Dark stars might sound like something out of a sci-fi movie, but they're not quite what you might imagine. First off, they're not black holes. While both involve dark matter, black holes are cosmic vacuum cleaners with gravity so strong even light can't escape. Dark stars, on the other hand, would actually glow powered by dark matter annihilation, not by swallowing everything around them. Another mix-up. Dark stars aren't just clouds of dark matter floating in space. Dark matter is invisible and doesn't interact with light, but dark stars would be massive, luminous objects, potentially thousands of times brighter than our sun. They'd be more like cosmic lighthouses, fueled by an invisible energy source rather than nuclear fusion. And here's one more myth to bust. Dark stars aren't the same as those eerie, failed stars called brown dwarfs. Brown dwarfs are too small to ignite regular fusion, but they're still made of ordinary matter. Dark stars, if they exist, would be something entirely different. A whole new class of object that challenges how we think about the early universe. So, to sum it up, dark stars aren't black holes, they're not dark matter blobs, and they're definitely not failed stars. They're a fascinating what if in astrophysics, a reminder that the universe still has surprises waiting for us. And who knows, maybe the next big discovery will prove they're out there after all. Now, let's take a step back and consider the bigger picture. If dark stars truly existed in the early universe, what role might they have played in shaping the cosmos we see today? Imagine a universe where these colossal, dark matter-powered giants weren't just fleeting anomalies, but key players in the grand story of everything. One possibility is that dark stars could have altered the timeline of cosmic evolution. Their immense brightness, fueled by dark matter annihilation, might have heated surrounding gas clouds differently than regular stars, slowing down the formation of the first galaxies. Or perhaps their sheer size and energy output accelerated the process, seeding the universe with the building blocks for larger structures sooner than we think. Then there's the question of their legacy. If dark stars were as massive as some theories suggest, their deaths could have been spectacular, collapsing into the earliest supermassive black holes, the kind we now find at the centers of galaxies. That would mean dark stars didn't just fade away. They might have laid the groundwork for the cosmic giants that dominate the universe today. And what about the far future? If remnants of dark stars linger in the modern universe, hidden in the darkness, they could still be influencing things. Their gravitational pull might subtly warp the paths of nearby stars, or even contribute to the mysterious dark energy that's causing the universe to expand faster and faster. But here's the most intriguing thought of all. If dark stars existed, they remind us that the universe's story isn't set in stone. There are twists we haven't imagined yet, hidden chapters written in the language of dark matter and ancient light. Whether they are gone forever or still out there, waiting to be found, dark stars challenge us to rethink not just the past, but the fate of everything. Now, let's slow down for a moment and imagine something truly serene. Picture yourself floating through the vast, quiet expanse of space, where the usual brilliance of stars is replaced by something far more mysterious. Here, dark stars glow with a soft, eerie light, their immense forms radiating warmth, not from nuclear fires, but from the slow, steady annihilation of dark matter. As you drift closer, the darkness around you feels almost comforting, like a cosmic blanket. These ancient giants pulse gently, their light flickering like distant lanterns in an endless night. There's no harsh glare, no blinding heat, just a soothing, otherworldly glow that seems to hum with quiet energy. The silence of space wraps around you, broken only by the faint, imagined whisper of particles colliding deep within the star's cores. Around you, the galaxy stretches out, its usual chaos softened by the presence of these dark behemoths. Nebulas swirl in slow motion, their colors muted under the dim light. Planets, if any exist here, would bask in a perpetual twilight, their surfaces bathed in the gentle radiance of a star that doesn't burn, but simply is. Time feels different here, stretched and slow, as if the universe itself is pausing to breathe. And as you let your mind wander deeper into this tranquil scene, the weight of the everyday begins to fade. The mysteries of dark stars, their origins, their secrets, no longer feel like puzzles to solve, but like lullabies sung by the cosmos. Their glow isn't just light, it's an invitation to rest, to dream of a universe where the unknown isn't frightening, but beautiful. So close your eyes, just for a moment, and let the darkness cradle you. Out here, among these quiet giants, there's no rush, no noise, only the endless, gentle rhythm of the stars guiding you toward sleep. As we return from our quiet journey among the dark stars, let's take one last moment to marvel at their mystery. These cosmic giants, born from the unseen power of dark matter, remind us how much of the universe remains hidden, waiting to be discovered. Their gentle glow whispers of a time before ordinary stars, a time when the cosmos was young and full of secrets. Thank you for drifting through space with me tonight, exploring these enigmatic wonders. Whether they are still out there, hidden in the darkness, or long faded into cosmic history, dark stars invite us to keep dreaming, keep questioning, and keep looking up. So as you settle in, let your mind wander back to those quiet giants. Imagine their soft light still flickering somewhere in the vast unknown, a reminder that the universe is always more mysterious, more beautiful than we can fathom. If you enjoyed this journey, don't forget to like this video and subscribe for more cosmic stories to unwind with. Hit the notification bell so you never miss an adventure into the stars. And tonight, as you close your eyes, may your dreams be as boundless as the cosmos itself. Sweet dreams, fellow stargazers.